And this follows on pretty much directly from hashing and hash functions that we had yesterday. Hash-based data structures represent a crucial part of blockchain technology, Web3 technology. They're the underlying thing for Bitcoin, Polkadot, Git, like many of these distributed systems, decentralized distributed systems, really make a huge amount of use of these things. So it's crucial for you to understand, get a solid grip on them. When you're doing, sort of dApps or whatever, you're building stuff on top, you don't necessarily need to know too much about them. But certainly if you're diving into the systems that host these things, Substrate, Polkadot, you're going to need to know a huge amount about these really in depth. And even if you are building dApps, there are a lot of things, a lot of nuances with when you're designing these, dApps, whether they're smart contracts or palettes in Substrate, or any other, module in an app chain. This, knowing how these work and knowing why they might go slow, why they might go fast, why they might be insecure. Knowing that stuff is crucial in designing a dApp that's actually going to stand the test of time, that's going to work well, that's not going to fall on its face when it gets the 10,000th user or whatever. All right, so we covered a little bit of this yesterday. Hash-based data structures are a bit similar. I often have an equivalent pointer-based data structure. Why? Well, because pointers and hashes are on a sort of abstract level doing a pretty similar thing, right? The difference is that a pointer is pointing to someplace in memory, right? As of now, within some time constraint. Obviously, if the computer gets turned off, then it can no longer be, it's no longer meaningful to point to that place in memory, right? Whereas a hash references data in the same way a pointer points to a place in memory, referencing data, but a hash references data by its content and the hashing algorithm, but we assume that stays the same, right? We assume that's well defined at the beginning of time and it just stays the same to the end of time. So a hash references by content compared to pointers, which reference by position in a system, in an ongoing system. And you could add a URI here. A URI is kind of similar to a pointer. It references information by where you can download it from, basically, or where you can, in a manner of how you can get hold of it, in a similar way to a pointer doing this with the assumption that you have access to a particular machine's memory, and on the assumption that that machine's memory is not going to sort of be wiped. Since between the point that you're giving the pointer and when you actually want to use it. In principle, you could build similar data structures with URIs, but people don't, because URIs are super cumbersome and they're not especially effective ways of delivering data. An interesting difference between referencing information by its content versus referencing information by its location or position is that if you're doing it by its position, you can have cycles. Yeah, you can have a piece of data which returns which stores or references another piece of data which is itself, right? You can actually have like a one item cyclic linked list. Yeah, that's possible. It's not possible if you're referencing through the content of the data, right? Just think about it. If you're referencing through the content of the data, then you are now creating a self-referential, like through a self-reference through content. Like, what would it be? It's like like which came first, my reference or myself? There's no way of reasoning about it. Whereas if you're doing it by location, then you can mutate it. You don't need to answer that question because you first create an item that has no reference, that has no internal reference, and then you point it to itself. But you can't do that if you're doing it if your data is defined by its content. Yeah, because there is nothing. You could maybe create the datum that has no reference, but then if you try and mutate it to a datum which references itself, there is nothing to reference it to because that thing hasn't yet been created because you can't create it. Yeah? All right, good. A long way of saying that if you're dealing with reference-based data structures, if you're dealing, with content reference-based data structures, they cannot be cyclic. All right, so hash chains. Hash chains always go in this direction, right? You can't forward reference in a hash chain. That wouldn't make sense. You can only reference stuff that already exists. Yeah? That's already well defined. So you can never have like a doubly linked list. That would be hash. Yeah, it's like we define this, and then we reference it by its content, but we can do that because it's well defined. Yeah, but if we ever wanted to link this way, well, this would alter the definition of this, so this reference would become invalid. Like changing this would change this reference, making it invalid. So you just wouldn't be able to do it. Basically, it would make it cyclic. So it's one direction only, and we start at the left, and the references go always towards the left. Now, the equivalent of a hash chain for trees is actually a Merkle tree, right? Named after Ralph Merkle, who figured it out, thought of him, I suppose. This is pretty similar to a binary linked list, binary pointer-based tree. Nothing special here. The main difference is, these arrows are, these arrows are okay. Yeah. So we start with this node, and then we reference these two nodes from it, basically by just like hashing them, right? All the way down to the bottom. So this node references that node by hashing it, and so on and so on. So this node is basically contains some data, probably hashed, and this node references that by hashing this item, all the way to the top. Which means, in terms of causality, like cause effect, this one will cause an effect on what the value of this one is, but this one will not cause an effect on what the value of this one is, right? These bottom layers come first, and they make the next layer up, and the next layer up, and the next layer up. Right, so these arrows are actually wrong. These arrows should be in the other direction, right? This one came first. Is that right? No, sorry, ignore me. These arrows are correct. Yeah, fine, all good, all good. Now, proofs. If we go back to the cause and effect, this one causes an effect on this one, which causes an effect on this one, on this one, on this one, right? These two define what this one is. Yeah? These two define what this one is. Okay? Which means, because of this relationship, by extension, these guys all define what this one is. No more, no less. To know what this one is, you can calculate it just by knowing what these guys are. Yep. That way, in this way, the root, or head, if you want, trunk, the root hash, which is basically hash of this one, it's a commitment to the whole thing, right? It is defined by the whole thing. Oops. So all of this thing, I mean, but it's all by extension, so it's all super recursive. But all of the data structure defines this thing, and in fact, because all of these guys are defined by these guys, and so on, it's actually just this information which defines this. Yeah, because you can't change any of these without changing these. Now, the clever thing is that we can generate a proof. What does a proof mean? Right, well, there is a hash of this one. And we're already happy with the idea that this one is defined by, like its value is determined purely by these. Therefore, this, as we've said, is a commitment, yeah, to these. If we say, if we assert our tree has a root hash of X, whatever that is, we are asserting that its leaves have values of A, B, C, D, E, whatever the values of these things are. Yeah, there is no other tree that could have a hash of X. There is only one, because of how we've defined our hash function. Right, it's a secure hash function. Yeah, so there's a one-to-one relationship in practice. Therefore, if this is one hash, then these two must each be some hash and some other hash. They can't be any other hashes. And these four, therefore, have to be some particular 4 hashes. And these 8 have to be some particular 8 hashes. And these 16 have to be some particular 16 hashes. Right? And for now, we'll assume we're not interested in any of this data. We are interested in the leaves. So, moreover, the order must be preserved. So it's not the case that this could be A, and this could be B, and this could be C, and this could be D, and this could be F, right? No. This has to be whatever this is. This has to be, we'll define it as A, but this always has to be A if this is X. This always has to be B if this is X, okay? Good. So if we commit, if we assert that this is X, this is some particular value, we basically assert that the tree, the contents of the tree, the contents of the leaves particularly, are particular values, whatever the values should be, ought to be, for when the root is X. It's not the case that I have a tree that could be X and have values A, B, C, D, whatever, and someone else could have a tree whose root is X, but their values are like H, I, J, K, L. That's not possible. That would mean our hashing cryptography is broken. Yeah? Good. It's important. I'm hammering it in, I know, but it's really important to understand this this stuff. Okay. So because of that, we can do things like generate proofs that if we believe that the root is X, that this leaf here is D. Right? So if for whatever reason someone has come to believe that there exists a tree in the mathematical universe whose root is X, then someone who has access to this tree, or at least a certain part of it, can prove to me, who knows nothing other than the root is X, they can prove to me, beyond all reasonable doubt, that leaf of index, I don't know, number 4 or 3, with counting from 0, is D, whatever D happens to be. Right? But they can tell me what it happens to be, and they can show me that it must be true if I believe the root is X. Proof. And I'll underline it in case it's not obvious. This stuff is absolutely crucial tool for building trust-free, trustless systems. Yeah, it's a super important. It's the bread and butter data structure, right? So let's talk a bit more specifically. Suppose I don't know A B C D. Let's call this one M, right? So this node here has some data in it, M, right? And that we're the root X. How do we make a proof? Well, one way of doing a proof is just to tell our recipient, well, this one is A, and this one is B, and this one is C, and this one is D, and this one is E, and so on, right? But these things could be gigabytes big, yeah? And we don't really want to have to give them a terabyte hard disk to prove that this item is the Matrix 1998 original DVD release, right? No, that's not so useful. Much better would be if we only needed to give them a subset of the tree. And it turns out you can do so just by giving log n, in this case log 2 of the nodes, or order log 2, I should say. It's actually 2 log 2 in this case. 2 log 2 minus 1. So how do we do it specifically? Well, they know what this hash of this thing is, but we give it these 2 hashes, right, which make up this node. So this node, like the data in it, is really just 2 hashes. It's the hash of this node and the hash of this node. So we tell it what these 2 nodes' hashes are, and so on, and so on, and so on, until we get to the bottom. And then we tell it what the pre-image for this is, so we tell it whatever, I don't know, M is. Like we give it, we pass along the Matrix 1998 original DVD release data, right? So there's a DVD somewhere sitting under here. And we give it all of these hashes. And just from all of these hashes, we can check, right, well, firstly, does the Matrix DVD hash to whatever this thing is? Yes, good, okay, that's a start. We've got this hash, so we concatenate them into this node, and then we check to see whether these 2 hash to what this thing is expecting. Yeah? And if it does, then we're good, and we work our way up. So now we have this one's hash and this one's hash, and we concatenate them, and we check them to see if these 2 hash to what this link here is expecting, to what this node should be. Yeah? It is. Then we have this hash now, and we combine it with what this node's hash is, which is what this node should be, and we check to make sure this node's hash is these 2 hashes concatenated and hashed. And we do the same here to the top. And if all of these hashes check out, if we can basically rebuild the tree to the top and get the final hash X, which we already knew, we trusted for some reason. We won't say how. Maybe it came from a friend, maybe it came from maybe it was voted on by some decentralized system, who knows. But anyway, whatever this hash is, if it is the output of the hash, of running the hash function on these 2 hashes, then thumbs up. And it turns out that the tree of root X has on the 16th child node the Matrix original 1998 DVD release. Good. In reality, we don't need to be provided with the hash of these white ones. We actually only need the hash of the purple ones because we can calculate the white ones. So we calculate this white one from our Matrix DVD, the hash of it or whatever, And then we combine these two hashes, we hash them, and we get this one. And we combine these two hashes, hash it, get this one. These two hashes, hash it, get this one. These two hashes, hash it to get this one. And we make sure that this final hash is X. If it's not X, then something went wrong somewhere, and we disregard, the proof was wrong. We don't care why it was wrong. We just know it's wrong, and that's fine. But if it is X, then we know it's good. Right, why does this work? There are two reasons why it works. The first is, the fact that there can be no other trees with X. But the specific reason why the proofs work is because these purple things are the proofs. These four purple things are the proofs. Yeah? They constitute the proof. Why can we believe the proof is secure? Well, these purple things, these purple hashes, we assume any attacker could not provide us with purple hashes such that at the top level at least, whatever this value turns out to be could be hashed with this value to get X, which we already trust. Yeah? X was determined, we will assume, because we trust it, from a real tree. If they want to convince us that X means something different than that tree, then they would have to come up with a purple hash, like a purple, whatever this hash is, such that when combined with the result of these two, it got the same X. This would basically be a pre-image attack, right? And we've decided that secure hash functions are resistant to pre-image attacks. And when we say resistant, we don't mean like water resistant, like watches, where you go down 10 meters and you get some water in and it's broken, right? We mean cannot be attacked even by a government level attacker, right? We mean like the mathematical definition of resistant. Okay. So this data structure is now, it's not something that is ephemeral in the same way as typical like pointer-based data structures, such that when you turn the computer off, they're gone. It's not even like a data structure that exists in replication on many different machines. Yeah, you sometimes get these kind of ways. What is it? Open? I can't remember. But anyway, there are like operating systems that basically exist in replication on many different machines, right? And if one machine goes down, the operating system stays up because it's replicated all of its data structures across many different machines, right? That's one way of sort of saying, oh, well, this is sort of a more permanent thing. It's more permanent. It's not nearly as permanent as this. This, until the crypto becomes like, I don't know, compromised, until it's broken, until someone can create at will another purple node, another hash here, such that it hashes with this one to the same X. Until someone comes up with that, then this is timeless, right? This is just fundamentally persistent. Turning off any number of computers will not matter, because this is the only tree with a root of X that is known to mankind, and that until the crypto becomes compromised, will only ever be known to mankind. Yeah, aliens could come discover a deserted Earth, but find a Merkle root of X and discover the same information through, I don't know, brute forcing, whatever. But like, it means the same regardless of who is looking at it, because it's defined purely by logic. Yeah, it's not defined by what happens to be at some memory location in some computer, however well distributed it happens to be. Okay. When we're making this proof, so this is a 16-leaf tree. Yeah. Each junction it has 2 nodes. Yeah? So it's binary tree. The proof size is therefore, you have to do 1 for each column. It's perfectly balanced. Yeah, crucial thing, it's perfectly balanced. And if it's perfectly balanced, then the proof size is basically 1 hash for each level below the root. Yeah, so mathematically, it's log base 2 of the number of child nodes. In this case, 4. Yeah, 2 to the power 4 gives you 16. That's really good. Like log complexity it's not, you know, it's much better than having to give all 16. It doesn't grow very fast at all. There we go. And as it turns out, if you update a leaf, you need the same amount. So if this changes, then you need the same amount of hashes to show to demonstrate what the new root is. Okay, so that's a Merkle tree. Now, how do we use them to make key-value databases, and what are the pitfalls of these key-value databases? So I presume everyone's pretty familiar with a key-value database. Nods of heads, yes. So as a data structure, maps a key to a value. Generally, keys are, well, they might be variable length, they might be fixed length, whatever. We want to be able to add new pairs to this database. We want to be able to modify information that's already in there. We actually want to be able to remove it. I don't think that's written down, but never mind. For any key, we want to demonstrate, we want to be able to prove that it's in there with a particular value, and we also want to be able to prove if the key isn't in there at all. Okay. That's the kind of database that we're wanting to build. That's the functionality of it. Okay, so let's define a few data structures, because I think probably not everyone is familiar with all these terms. So trees, pretty familiar with trees, I would hope, but they're rooted, so they have a single root. Undirected, so the arrows can only be in one direction. They don't contain a direction, right? They're always, going down from the root or whatever. Acyclic, right? Can't form a ring. Graphs, nodes with arrows. Merkle trees are trees which use hashes as the arrows, as the links, right? They use hashes in order to reference it. Pointer-based trees use pointers. Merkle trees use hashes. Familiar with these two. Tries are a particular class of tree. All right. Basically, a trie is a tree where if you're looking for a piece of data inside of it, you already know which route to take through it by virtue of knowing the data. Yeah, there are trees where that's not possible. There are trees that store the same data in different positions depending on what other data is in the tree, or depending on, there are trees that determine where a piece of data should be located depending on what other data is in the tree, or depending on what actions have happened first in the tree. Yeah. Tries don't do that. Tries are sort of more dumb and more simple, more constant in that regard. They always, at any given node, you will always know which child to go down to or not, just to stay at the node, depending on what that data is. You don't need to look at anything else. There's no other context needed. Okay, radix tries are a particular type of try, very simple type of try, and the location is basically determined by one digit from the key at a time. So you basically pull the prefix of the key off, and you look at its value, and you choose the child depending on what that value is. And then there are Patricia tries, which are a variant of radix tries that have some optimizations, basically to avoid having to go down, having to look at too many different paths. Because, of course, each time you go down a link, you have to look up a new hash. And hash lookups are slow. And, of course, you add an extra hash to the proof. And that can become costly. Yeah. So we want to minimize the distance between the root and the leaf. And by doing so, we minimize the proof size, and we minimize the number of database lookups. Yeah, clear? Good. So Patricia tries are just a way of optimizing that. So here's an example of a radix try. It's a radix try, basically of a key value database. It's very, very simple. With whatever, 6 words in. And it's doing it one character at a time. We're missing out the child nodes of the characters that are not that have nothing in, right? We're not. It's a sparse tree, yeah. So we're not bothering putting, I don't know, lowercase s right here, because there isn't, nothing exists down that path. We're just eliding it. Okay, so you got T, and if you go down T, then it turns out there are 4 possible words there. But T isn't a word, so yeah, T isn't a word. But we have, if you go down from T, there's the next possible letters are O for 2, and that's actually a leaf, and then E for T, TED, and 10, so te. And then you've got T, TED, and 10. Okay, easy. A is just a word on its own, so that's a leaf there. And then I comes down to in. And this is just a lonely path, right? So we're having to go to do one hash lookup, another hash lookup, another hash lookup. So 3 database lookups to get to in, which is a lot, really, for just one, when there's only one thing at the end of it. And if we were to prove that, this is indeed in, when this is whatever hash it is, then we would have to provide, we may have to provide, looking at this, we probably wouldn't, because we'd just be able to hash each one to get all the way back. We'd only have to provide these 2. But depending on precisely how our try is implemented, we may have to provide hashes at each of these levels. Okay. A Patricia try simplifies it a bit and allows us to basically combine lonely paths into a single node. So it just allows us to say, oh, and by the way, if you get here, it's always got these letters tacked on. So you follow the path down to I, and then it would say, it's also got N and N. So and everything at this path always has 2 N's following it. Okay. Good. And otherwise, I think nothing else has changed, has it? No. So that's basically the difference between a radix tree and a Patricia tree. There are other variant, like this isn't a especially strictly defined data structure in the same way that a radix tree is. There are different variants of the Patricia tree. I'll try. Ethereum has its own variant, Substrate has a variant, and obviously the formats differ as well. So, but the main point is that it contains optimizations to try and make these paths be minimal. Okay. Now, working with a Merkle-Patricia trie, so a Patricia trie that uses hashes as its links. If we insert any old data, we may end up with very unbalanced routes, right? It might take, I don't know, 12 things to go down one path, but only one to go down another. And this is this breaks our expectation of log n proof size and database lookups, yeah? If it's not properly distributed. This has, I don't know what, 2T, 10. Okay, yeah, 6. So this has 6 words in, and it's a, well, okay, it's not even base 2. Nah, that's a bad example. But in principle, our log n is based very much on the assumption that it's uniformly spread, highly balanced. And if we don't get that, then our proof size will only be bigger. Yeah, that's the optimum. As we move away from that, proof size get bigger, database lookups get more. How do we make the key size, the keys be more likely to be uniformly spread, and therefore the tree to be more balanced? Well, one way of solving it is to pre-hash the keys. So instead of there being any old data in the keys, there is now strictly random data in the keys, right? Uniformly spread data. I mean, it's random to the degree that our hash outputs data with a uniform spread of like zeros and ones amongst its bits, and to the degree that it's difficult or impractical for an attacker to construct pre-images for those hashes that would bias the spread of those zeros and ones, but you know, hashes do try to do that. So, the main point of this is, it's an example where partial collision, not full collision, but partial collision, matching a substring, or finding hashes whose substrings match, is resistance against that is important. Because if you can make a substring, or a prefix in particular, match, then you can start, bulking things towards the bottom with a few bits spread up at the top. And as you do that, you force the proof size to be much larger than the number of items, than log of the number of items in the database. Yeah? Because basically, you're going to have to go down a lot deeper to prove that an item's there, or the value of the item, or just to look it up from your disk-based database, just to look these nodes up. Good. Okay. So we want to really minimize partial collision. We want to maximize uniformity, and the hash algorithm, a good one, will let us do that. An insecure one, like 2x, will not help with that much. Yeah. The only reason a 2x, something like 2x, an insecure algorithm will help is if we know, I mean, it's kind of random. We saw 2x in the code, in the live coding, right? It looked kind of random. It didn't look like the input I was putting in. But, you know, if an attacker controls that input, they can create different inputs such that they do look more or less the same. They may be even completely the same. So we should only use 2x to hash our keys if we're certain that they cannot be controlled by a potential attacker. And there are a few instances, but not very many, where we can do that. Okay. Next question. All right. What I've described to you as a log is a radix 2 tree, right? Radix 2 trie. So 2 items at every point. Not this one, but this one. Yeah. That's a 2 binary tree. So if we're doing a Merkle-Patricia trie, how many branches should we do at each level? Big question. Well, we know the proof size is the number of nodes, the number of leaves, multiplied by the basically all of the other nodes left at each branch, right? So in this case, it's log of the number of leaves, which is 4, log 2 of the number of leaves, log base this radix of the number of leaves, multiplied by the number of leaves, the number of nodes at every level that is not this node. So it's basically, in this case, it's 2 minus 1, right? 2 nodes, we know one of them just from calculating from its children. So it's 2 minus 1 multiplied by log to the base 2 of 16. Yeah? In this case, 4 log to the base 2 of 16 multiplied by 1. This is one node that we don't know at each level. If we have 2 nodes, branch factor of 2 nodes at each level, then we get the smallest proof. But when if we increase that, we reduce the number of branches that we will typically have to go down. Yeah? Because we cover more ground with each branch. So if we increase that, for example, to 16, then on average, we'll only have, for something that's like, I don't know, for 256 entries, if we have a branch factor of 16, we'll have to go 2 levels deep, if it's perfectly balanced, yeah? Go down 1 and cover, and we have 16 children, go down the next one and we would have 256 children, so it's 1, we're done, yeah? If we're a branch factor of 2, then we'll have to go 8 levels down before we get to children, before we get to a leaf, yeah? Now, it's only 8 levels of 1 hash, but it's still 8 levels, which might mean 8, well, firstly it means 8 hashes, right? We have to do 8 hash calculations. They're usually fast, so we're not usually too bothered about that. But it may also mean 8 database lookups, because we have to look up what that information is 8 times. And going to disk, if the database is on disk, could be quite slow. So it's, whereas if we have the 16 at each thing, we're looking at more redundant information each time, because we're looking at potentially 15 other hashes, so the proof size goes up, and the individual database read size goes up, but we only have to do it twice. And we only actually have 2 hashes to compute of more data now, 16 child hashes when we want to hash its parent, but still, hashes are fast, so we don't need to worry too much about that. And as it turns out, reading consecutive data from disk or memory is also quite fast. So it's not that it costs 8 times as much to read 16 hashes as it does to read 2 hashes if they're right next to each other in memory. So performance is a it's basically partially a trade-off for, do we want the smallest proof size, or do we want the fastest proof generation and usage on a node that stores everything, like on a database on a full node, a node that actually has the full tree that is storing the full tree. And it's not always clear where that should fall, which one is more important. As it turns out, a branch factor of 16 is not bad. It's a pretty good trade-off between 2 and 256, say. And that's just found from empirical testing, just like looking at how the different trees perform on typical data on typical hardware. But, as hardware changes and as usage changes, and for that matter, as our understanding of how to implement this stuff changes, like software becomes better, it might very well be that we move in one or the other direction. In particular, we're increasingly becoming dependent on light clients. Light clients are things that need almost everything proven to them. And therefore, proof size can become increasingly important over strictly performance or proof generation performance. And in that case, we would probably want to reduce this branch factor. Okay, that's Merkle trees. The next little data structure we're going to talk about, Merkle mountain ranges. They sound a bit scary, but it turns out they're actually quite simple. They're a sort of adjunct to Merkle trees. And they basically allow you to build Merkle trees progressively in an append-only fashion. So they're good for sequences, where you have a sequence of things, you want to keep adding more things to it. You don't want to alter what has already gone before. Yeah, so they're not very good for mutating existing information in it, but you can add more stuff to it, and you can get a constantly changing root. Yeah, that means all of the stuff that has been added so far. Yeah. So you start with the empty root, and then you add one thing to it, and you get a single item Merkle tree. So basically, the root is just a hash of that item. You add something else to it, and now you have a 2-leaf Merkle tree. Yeah, and the root is the hash of those two, the hash of the hashes of those 2 items, and so on. So let's have a look. And the cool thing is that with the hash works in exactly the same way as a regular Merkle tree's hash, in that you can prove that at any particular index there is a particular item, and that is a log n proof. Like Merkle mountain ranges will tend towards being perfectly balanced. They won't always be perfectly balanced. It will depend on precisely how many items there are in there, but they will not be extremely unbalanced. Like the balance, the amount of the worst case is pretty good, right? Okay, here's an example of a Merkle mountain range. So it's created. If you look at it, it's 3 Merkle trees. Yeah, and you will always have some limited number of Merkle trees. Ideally 1. In certain cases, just one Merkle tree. Basically, in this case, when it's a perfect power of 2. So if you had when the number of leaves, the number of elements that have been added so far is a perfect power of 2, then you'll end up with just a single Merkle trie. And as you have non-perfect powers of 2, you'll end up with multiple Merkle tries. Merkle tries. So this first one hosts the first 8 items. And then this next one hosts the next 4, and so on down. They always have incrementally fewer items, like incrementally lower powers of 2. This final one, there's only 1 item left, so that's just a trie of 1. Now, when we add a new item into this sequence, 14, we will make a new trie of 2 items, yeah, and it'll have, the hash stored here. That will be it. When we add a 15, then we'll just have, 13 is just a lonely item on the end, 15 will be a lonely item on the end, yeah? And then finally, when we add 16 will join with 15 to make a trie of 2, but then of course, there'll be 2 tries of 2, and you're not allowed, one of the rules for Merkle mountain ranges, you're not allowed to have 2 tries of the same order sitting on the end. If you do, then you join them into 1, you make a new root. So these two pairs, these 2 item tries, will become a new 4 item trie. And then of course we've got 2 4 item tries on the end, so these will become a new 8 item trie. And now we have 2 8 item tries on the end, so they'll become 1 big 16 item trie. Yeah, and as I mentioned before, 16 is a power of 2, and so we will end up with just 1 trie in our mountain range. Yep. Why is it useful? Well, basically, because when we add a new item on, we constrain the alterations, the new amount of hashing and node creation that we need to do, to log of the number of items. So it's a heavily computationally constrained operation. It always tends towards a balanced trie. So it's nice and easy to reason about in terms of performance and proof sizes. That's it. But those 2 are very important points. There we go. So we have 13, we have 14 on, we've got this 2 item thing. And then it's reasonable with these tries, these orphan tries, that we will just put these struts in to make a root. Yeah, just makes proving easier. Rather than having to store 3 roots, we just store 1 root. But we have to have these sort of nasty, not improper sort of binary things, but that's fine. More of an implementation point. Okay. Merkle mountain ranges and Merkle tries. Any questions? You want to shout? Yeah.
Now, there was this assumption of the tree being perfectly balanced because you are inserting, say, uniformly random hashes.
Mm-hmm.
Now, it's a bit of an optimistic assumption.
Yep.
Because I expect that even if the hashes being inserted are uniformly random, the resulting tree will not be perfectly balanced. There will be maybe some branch with n layers, some with n plus 3 or something like that. Has someone done the math on questions like within 95% probability, the amount
I don't think anyone's really run the numbers, and maybe it would be a fun exercise to do that. But the difference between log n and n in terms of complexity is very far, and like if something is uniformly random, although it won't be actually uniform, it will be much closer to actually uniform than it will be to all vaguely super biased. And you would need it to be all super biased to get much closer to that order n than you would for the order log n. So just on my gut feeling is that it's going to be very close to log n if it is very random data. It won't be precisely log n, sure. There will be some extra component in there, but I don't think it's going to be an especially significant one. Yeah. But I know, as far as I know, no one has given any like calculation, any final formula for determining precisely what, how much more than log n it will be.
You mentioned in the Merkle mountain ranges in the examples on the sketches on the screen that they're a power of 2. Like whenever there's a new route, then they merge and it becomes the next Merkle mountain range. Mm-hmm. The last picture though was showing that the 13 is connected as the Merkle mountain range, and that's kind of confused me.
Yeah. So this is how Merkle mountain ranges will be done typically when implemented. Basically, you take this should be outlined in red, right? The red ones are the individual, properly balanced, like full saturated Merkle tries. Yeah. So we only deal in saturated Merkle tries. Now, you can make a proof that an item of a particular index is in this sequence through knowing the hashes of each of these 3 saturated Merkle tries. Fine. That's like first step. And that's the important step, because with this, we have a clear knowledge of the complexity. So firstly, the trees are balanced, great. Secondly, it's a very computationally constrained operation when we are adding an item, or for that matter, removing an item. Fine. Now, it turns out that having potentially log n items, log n routes to manage, like for the commitment to be log n hashes, is a bit of a pain. It'd be easier if it's just one hash. And so what we do is we add these extra nodes in that we're basically forming an unbalanced binary trie from the Merkle roots, yeah? And we end up with this overarching irregular trie that's not part of these main sequence of tries that just give us one single hash. And then we have a single hash for the commitment to all of this structure. But we do that sort of as a step after we've modified the mountain range. Like, this is the mountain range, like these 3. And when we modify them, when we add a 14th element on, we just drop these 2, right? These 2 no longer. It's not like we try and persist these in the same way that we persist everything else. Yeah? These 2 are just dropped. We add the 14 on. It turns out we have 2 of the same order, so we make a composite one. We root them in the same Merkle root. Yep. And then we end up with still 3, and then we add the scaffold on to give us one final root.
So it's like a temporary commitment until the next.
Yeah. These nodes don't persist when we add successive items. They're just there so that we can have one hash as a root, one single root.
Yeah, question as well. Can we add some daemon nodes in the tree? to make sure that it's uniform, balanced?
Can we
Like
add?
like some dummy nodes.
Oh,
like
dummy nodes.
Pod the 3. Yeah.
Like in here, you mean?
Yeah.
Yeah. Yeah, you could. It would be, I guess, another way of doing it. But, I mean, it's... So essentially, you would have a root that is 16... you would always have a tree of 16 items, and then you would always define this one, and always define this one, and then this one would actually, you'd have a separate child here, and then that separate child would have another 2 children, and that separate child would have another. You could have those nodes and fill them up as you go along, but the tree would have to be a little bit more complicated because you'd have to introduce what an empty node was, like a dummy node, and separate it from a node that just happened to have no data in it, for example. Mm-hmm. So you'd complicate things, I think, a little bit. And you'd also potentially have to store these nodes as well, so it would become a little bit more bulky. You'd be using up a little bit more space. You possibly have to hash them, so you potentially be adding a bit of extra proof size or a bit of extra database lookup or whatever. I think it would probably just end up with a bit more complexity.
Thank you.
So you'll hear people talk about, in order to, really decentralize a chain in the future, that not only people can run nodes with servers, like I want to be able to run a node on my phone. And so I think that's where Merkle proofs come in some. So like the phone can't store, hundreds of gigabytes for the whole chain, but it can store a Merkle copath and be able to work just with that.
Mm-hmm. Yes. So, I mean, Merkle proofs are crucial for low power devices, for like resource constrained devices, to work in a trust-free fashion. At the moment, on major platforms like Ethereum, they like low power devices, and we basically include all non-server devices in that category at the moment, require a node, an RPC node, basically a server to go to serve them information, usually in a fully trusted fashion. They just trust that this is giving them the right information, this server. And that's obviously, that breaks Web3. That breaks the entire premise of Web3. There is like a server that everyone's going through that they trust. It's like, well, that's just Web2. Right? I mean, all right, anyone can start a server. That's a really good thing, but still, if the practicality is that you don't want to start a server, and most people are therefore not starting a server and just going through a public server that is run by a self-interested corporation or whatever, then it's problematic. So what this allows you to do is to not have to trust these nodes that store more information than you. Because they can prove everything that they say. Yep.
Could you please talk about directed acyclic graphs versus undirected acyclic graphs, and maybe what the use for each would be? Because I've heard of certain projects claiming that they can decentralize with directed acyclic graphs strictly.
Okay. I mean, very, very big branches of computer science, like graph theory, or mathematics even. So, I mean, I can't really go into much detail. The two are not directly comparable in this instance. In sort of the cryptocurrency space, when people say directed acyclic graphs. Let's bring one up. Okay. And people say directed acyclic graphs. They're basically meaning a blockchain that can fork and rejoin, right? They're really sort of talking about a hash chain, but where, this can reference two parents, and so on, but then they can all rejoin in some very chaotic fashion later. And when, in that case, these don't necessarily need to be blocks of transactions, they can actually be single transactions. So we can start imagining transactions that reference other transactions as a way of bringing themselves into a global transaction cloud. There's a big problem with it. Well, actually, there's two big problems with it. The first is consensus. There's no guarantee that by referencing some transactions that have gone before, that your transaction will become part of a global consensus, like part of an irreversible ledger, an irreversible record of this transaction happening and not some other mutually exclusive transaction. Transactions could happen simultaneously or apparently simultaneously. For example, you might have 4 transactions going here, 2 mutually exclusive ones, and it might not be that they are mutually exclusive in terms because they are malicious, they're double spends. It might be that they're mutually exclusive because they alter the same state. Yeah, it could be that I'm using some smart contract and it increments the counter. One of them, they both increment the same counter. Well, if they both increment the counter and they both do some reasoning based on that counter, maybe it's an index used for a database entry, then, well, they can't both do it at the same time. Otherwise, they'd end up making 2 entries with the same index. Yeah? And so there are some things for which sequential guarantees are absolutely required. And DAGs, in their very parallelized fashion, won't work well with that. Similarly, if we want global consensus is very, you can argue it's not necessary, but it's very, very useful. It's very useful, for example, with interacting with other consensus machines. Suppose you want to build a bridge to Ethereum or something, right? You want to build a bridge. What is it that you're bridging? If it's a DAG, you can't bridge every transaction over because there could be a potentially unlimited number of transactions. That would be an unlimited amount of data that you have to pump in. You need to be able to commit in some way or another to a world of all of these transactions, right? And that's basically what we've been talking about with Merkle trees. By committing to this hash, you're actually committing to this entire data structure, this entire world. These could all be transactions. So by committing to this hash, you're committing to these transactions. Well, you can't really do that in a DAG because there isn't a root, right? It's not a tree, it's not rooted. So you'd have to bring in every transaction individually, which is a huge amount of data. Plus, you don't really have any way of trusting each transaction individually. How are you going to trust it? It's there is no global consensus on which transactions have happened and which ones haven't. There is just a cloud of things referencing each other. So it makes that kind of thing very, very difficult, if not impossible. The advantages are parallelization and potentially scalability. But so far, there is no indication that DAGs can work in practice. The DAGs that are out there use heavily centralized band-aids in order to actually make the transactions, actually make them vaguely practical. They run basically a server that creates new transactions whose job is to reference all of these random other transactions. So basically they're producing blocks. They're a regular sequential blockchain, right? Referencing transactions with their super transactions. Like the super transactions basically just take the position of blocks in a blockchain, and everyone else's transactions, basically by submitting them, they're almost like submitting them into the transaction pool. So, yeah, I don't know. I think it's an interesting like direction. I think it probably deserves more deserves attention. I think there's like experimentation that can be done, and maybe there is some middle ground between a DAG and a regular blockchain that would allow some of the like scalability of a DAG and flexibility, but still not compromise the ability to have global consensus and sequential actions like smart contracts when desired, like as with a regular blockchain. But I think so far they're not very practical.
Thank you.
Yeah, so from my understanding, most people would just store the root hash of a Merkle tree. Then what would be the incentive for anyone to store all the data to then give to regular consumers who then need the data to construct the proofs? Where's the incentive there?
Okay, so there are two elements to this. The first element is, what's the incentive to store the data at all? The second element is, what's the incentive to share that data with someone who's asking? Well, what's the incentive to store data at all? It may well be that by storing data and utilizing that, for example, in the production of new blocks, or the creation of proofs of validity of particular state transitions, particular mutations of state, the blockchain pays you. Now, this is the case with most blockchains. Most blockchains, I mean, all the ones I know, pay block authors one way or another. They incentivize it. Bitcoin incentivizes it by giving you a bunch of Bitcoin. Ethereum incentivizes it by giving you some Ether. Polkadot incentivizes it by giving you some DOT, and so on and so on and so on, right? And in order to create blocks, you need to store that information. You need access to this whole Troy. Just because someone may end up, or the blockchain may end up using this data, and that data. If you don't have it available, you don't know what it is, so you can't create the block. Like, you can't possibly create a valid new block. You can't reason what that new block should be. And there's no way of sort of, I mean, with some data systems like Bitcoin, you might be able to reason that you actually don't need this part of the tree, only this part. Like, probably. You probably don't need this part of the tree, only this part. You might be able to reason that. But with Turing complete chains, where like anyone could, or the chain could decide that it wants to do anything at any time, you just can't make that kind of reasoning. So Polkadot, for example, you would be you would risk your utility, your income, if you're a block producer and you started throwing away bits of the blockchain, bits of the state tree that Polkadot has not sort of pre-authorized you to do. Like, Polkadot has not said, I don't need this anymore, throw it away. That brings us to the second thing. What's incentivizing these nodes that are keeping the whole tray to share what they know? Well, there's a few reasons. One of them is if they are making their income by virtue of this blockchain being active, and indeed by virtue of this blockchain, by the blockchain that they are on, the fork that they are on, being recognized as the canonical version of this chain, then they're incentivized to have as many other individuals replicate their view of the world, their state, their history as possible. I could mine Bitcoin on my own, and I could do really well. But if no one else shares my version of the Bitcoin world, my version of the Bitcoin blockchain, then what does it matter? My Bitcoin are worthless. I can spend them only on my own server. Yeah? I can only trade with myself. So there is an inherent incentive to share your view of the world. Almost like, in politics, it's like why people want to share their view of how the world should be, because they want to live in a world with other people that, like, I don't know, respect them and have similar views. And this like pushes people to try to convince other people to think like them. It's sort of the same, except within blockchain, there's an economic incentive that goes along with it. Now, this covers why nodes might want to share, might want to help each other sync up. It doesn't really cover why I necessarily, running a full node, want to share my data with, like, I don't know, light clients that just want bits and bobs, because light clients are not, they're not going to sort of go on to share their data with other people necessarily. I mean, if they only have one little bit of data that's specific for their query, unless someone else wants exactly the same query answering, they can't. What they have is not useful to anyone else. I don't think anyone's got an especially good answer to this, but most of the answers revolve around one of two things. Either there could be some form of micropayment, either made by the light client itself or made by the blockchain on behalf of light clients. The micropayment could be a payment channel. That's the most, that's a pretty complicated thing to set up. Could be a random, a probabilistic payment. So it could be that, like, basically a lottery ticket, and one time out of every 1,000, the light client would, a payment that the light client, or a ticket that the light client gives to the full node for answering a minor query would actually pay out. It could be it could alternatively be some sort of token that demonstrates the light client is part of some grouping that would not be able to, that has a constrained membership. So the main point is that we will assume that full nodes have a minor incentive to provide data to light clients because it helps push their idea of what the world should be, and therefore contributes a small amount to making their rewards valuable. But that's only a small incentive. And so the question is, how do we make it so that it cannot be, that incentive is useful for the network? We don't want to the degree, they may say, right, well, I'm happy to share, 1 megabyte per minute of proof bandwidth to light clients. We will assume that this is a minor cost. If it's a cost at all, it might just be in the noise of their overall bandwidth costs, and it just may be that this is an amount that they're willing to contribute in order to help make what their rewards are be worth money. The question is, how do we make that 1 megabyte per minute in proof bandwidth go to a good subset of individuals rather than one greedy individual and no one else? Because then if that were happening, it would have a minimal effect on making their rewards be valuable, and therefore they might start turning it off. So we can imagine the network backing the handing out of bandwidth to light clients, where the light clients are, maybe one per person who can use, maybe in a per person manner, where each person gets maybe 1 megabyte per day. But then we need to know what constitutes a person. And they need to be able to prove this to potentially the blockchain, because it could also be that the blockchain supports this. And it's actually not the full nodes, but the full nodes get paid by the light clients, and the light clients can claim their payment back from the treasury of the chain on the basis that the light client is controlled by a single individual and they're not abusing. Like you know, it's within some reasonable amount of bandwidth that they are using. I think it could also be, one other possibility, is that the chain, it becomes part of the rewards for like, you know, the staking system. So by demonstrating that you are sort of locking yourself into the economy, the system gives you back a sort of voucher that you can use with your light client. Yeah, so it's like, hey, look, I control this account and it's staking at least, I don't know, 100 DOT. Therefore, you can now, you get a free 0.5 megabyte a day on light client bandwidth. Yeah, and it just, you have your little, it's like maybe a separate token, or it's, I don't know, it's just something that gets topped up. It's like just a little counter, non-transferable. And then with that, full nodes can take these counters and sort of amalgamate it as it gets spent, and send it off to the treasury for payment back in DOT. Something like this. But basically, there is a sort of incentive for the network to for those who are servicing the network to spread their view of the world, right? So this is enough to guarantee that they will. Well, firstly, there's a definite incentive for those that maintain the network to retain the full database. There is a very loose incentive for those who have the full database and maintain the network, get paid in the network, have funds, are exposed to the network's token or a particular view of the network, to spread that view. And then finally, in principle, I think one can imagine mechanisms that would allow a reasonable use of humans to use the proving the network's overall bandwidth and proof generation computation, if it can be done in a way that, you know, somehow allows fair use. But precisely how that is, I think, is yet to be properly designed, and would certainly be made easier by some Sybil-resistant mechanisms, so basically some way of identifying who individuals are, without identifying an individual, a unique individual from another unique individual, not identifying what their name is or anything like this, but essentially an ability to hand out freebies to separate people and know that no one is benefiting significantly more than anyone else.
Great answer, thanks.
Do we have time for more, you think?
Yeah.
I had one maybe burning question to add to that. I would postulate that we could assume it's okay to ask people to have some reasonable amount of data. Maybe not today's standards of many, many gigabytes, seems like unlandish for your phone to have, but maybe some megabytes, and that will expand over time. Is there, much like in cryptography when we're talking about the probability is astronomical that we could have a failure, in same with data, right? Eventually we'll get to some point, and I don't know what this might be, that would be astronomically improbable that the history could be lied about beyond some point. At that point, could we discard some data? So effectively we would cap the size of the total history of the state, thereby enabling, it's not possible to go back to the genesis, but it is astronomically improbable that the state is incorrect?
Yeah, okay, so there are two bits of the data that a blockchain node would store. There's the blockchain history, which is the number, the total block, all of the blocks that have come so far since the blockchain began, right? So it's basically all of these guys, all the way back to the beginning of blockchain time. The other information that a blockchain stores is a trie, Merkle tree usually, which has the latest state, right? The latest snapshot of the database. Yeah. Now, actually, because of the way consensus systems work, it usually stores several of these, right? Maybe the last 100 or so blocks worth of these. And it's actually, it's because we don't change all of it every block, we only change, you know, a small subset of it. It's not like 100 times the storage of one, it's only a small factor beyond the storage of one. Like, in the same way that, you know, when you alter stuff on Git, it's not like every time you change a small part of a single file, it has to copy the entire Git repository, yeah? It only stores like little changes, and it does so in a very efficient manner. This works in the same way. Now, we have a type of node called an archive node that stores the snapshot of the state, the snapshot of the database, for every block in history. So this has one, and this has one, and this has one, and so on. This can get expensive, because even though the changes are relatively minor at every block, if there are 20 million blocks, before long you're having to sort of store the whole storage many times over. In principle, archive nodes are not really needed because you can always compute what the storage should be just by rerunning the chain up until that block, right? You just reevaluate. But that can take a very long time if you're on block 20 million and you want to know some storage item at block 19 million. You don't really want to have to recompute 19 million blocks just to find one storage item. But anyway, at the moment, that's sort of where we are. It's one or the other. You either have an archive node that like requires terabytes of storage, or you rerun the blockchain to the block that you actually want to query, and then and that would take 3 days. Like, you know, it's like kind of one or the other. Now, what you asked about is at what point can we drop stuff? So at the moment, we do drop the state after like whatever 100 blocks or something on Polkadot. So that's not too bad. We don't drop any blocks at the moment on Substrate, any historical blocks at the moment on Substrate-based chains. So if it's a 20 million block blockchain, we store all 20 million blocks. Each block isn't so big. It's basically just, you know, a header, which is like 100 bytes, and then a bunch of transactions, which could be up to like 4 megabytes, but usually it's much, much smaller. In principle, there should be no reason why we would keep all of the blocks on every node, because most of the time you don't really need to know what they are. We haven't written the logic to drop them yet. It's sort of on the back burner somewhere. The only issue is that if every node on the network drops the history, then you can, and no nodes on the network store the tree for these blocks, then you can never query what happened at block 19 million. You cannot recreate it, right? It's just lost to the ages. And that's not so good. I mean, it doesn't represent any immediate security issue, but it's not great not knowing how a blockchain came to a particular point. If there were some security issue, it could eventually just be kind of washed away And if some particular state happened because there was an issue in the logic at this block, but then we forgot exactly what that logic was and how that came about, and we could never recreate it, then it's like the perfect crime, we could never prove that it had even happened. This is the main reason why we don't drop historical blocks yet. There needs to be some way of the network guaranteeing that these things will be kept around, even if not operationally near. Like, we want to incentivize some archive system to keep them. They don't need to be available on nodes, but we should know that they are somewhere. And we're starting to get to the point where we can imagine systems like this, sort of Filecoin style systems, where we just incentivize someone to keep these things around, and occasionally we check that they are actually there. Maybe the first one to respond gets an apple or something. First one to respond gets a minor incentive. What else was I going to say? Maybe that was it. Yeah. Okay. If it comes back, I'll mention it. But yeah, hope that was roughly useful.
Yeah. Hey, great session. Just wondering, what do you think it's a likelihood that the end consumer or user will end up having light clients rather than using centralized RPCs? And do you think that'll be a norm across all chains? And something like Substrate Connect. And then number 2 is, can you talk a bit about zero knowledge proofs for privacy? Thank you.
Okay. Zero knowledge proofs for privacy. We'll get to that in the next lecture. Light clients. Yes. I mean, this is Alice in Wonderland, right? How far does the rabbit hole go? Where, at what point do people stop caring about the guarantees that we're trying to give them? I mean, it's not yet clear that the people do care about the guarantees we're trying to give them. Yeah, it's an assertion, it's a hope perhaps, but it's certainly not clear yet. And it may be that changes in the world, I mean, we're already seeing a lot of changes in the world, if you look at the last 20 years of history, bring people to the point of deciding that actually these guarantees are really important and we do need them. And personally, I think the guarantees are great, and I think people, it's worth persevering just in order to get the guarantees for themselves. But I'm maybe I'm a bit of an exception there, and I think maybe people need something a bit more tangible to make the argument. I think if blockchains are to become anything more than a way of a few corporations improving their back-end systems, then light clients will necessarily need to be mass used. Like RPCs, I think their day will come, my opinion, but I think their day will come over the next 5 to 10 years when regulation becomes tight. I think we will start to see centralized RPC providers restricting their services. I think we'll start to see, perhaps we won't see it necessarily, but I think it will start to become the case that centralized RPC providers will be regulated, will be required to toe the political line, will be required to, place on their systems filters, blacklists, possibly even white lists and grey lists, where they're required to delay transactions until a government or regulatory system gives it the okay. And I think we will, to a large degree, lose a lot of the, we stand to lose a lot of the guarantees that the systems give, censorship resistance being a notable one, but also others. And light clients are probably, I think, are a crucial, possibly the most crucial piece of technology. Maybe not the most, probably privacy is the most, but light clients are among the most crucial pieces of technology that can help guarantee, that can help make these guarantees real and persistent. So yeah, I don't really see a world of Web3 without light clients being used by basically everybody.
Hi, this is maybe related to what you were talking about earlier with being able to delete certain blocks. But could you talk a little bit about pruning the trie in the context of blockchains and how exactly that works?
Right, so this isn't really something that we do too much in Substrate. In Substrate, we try to ensure that all of these leaves are here on purpose. Like, we want them around. What does it mean for a blockchain to want something around? Well, it means either it's important to the functionality of the blockchain, or it means the blockchain is making money out of it. How does a blockchain make money? Well, basically, it requires somebody to pay. Place tokens in the treasury, whatever. A simple example would be transaction fees, right? Blockchain makes money from transaction fees because users, in order to send transactions, pay the fees, have to hold and utilize tokens. So, one way that Substrate, or in particular Polkadot, Kusama, and all the other chains manage this is by requiring, for user data, requiring that there be some associated value locked up, or basically some associated value paid. And the payment happens either through actually like some account being deducted from. This is rare in the Substrate world, but it is, I think, some of the smart contract stuff still has it in, or at least used to have it in. Or it's more likely it's that some balance is locked up, and that locked balance cannot easily be like utilized for other things. So it's an opportunity cost that is exacted on the participant, on the user, the agent, the attacker, whatever. Now, there are systems where you can't do this so easily. Smart contract systems, for example, if you require the smart contract to sort of pay for its data usage, it's the nodes in this trie, then eventually that payment, it might not be able to pay. And then what do you do then? You could say, well, we just discard the smart contract, like throw it away. Bit harsh, because then that might be like someone just forgot to make a payment one day, or it had more users than expected or something, and then suddenly the entire thing's blown up. So probably don't want to do that. That would be, it would be impossible to sort of recreate it very easily. So instead, we want to be able to prune, potentially, prune part of the trie, but be able to put it back again. This is like if a payment is made or whatever, if someone does something that makes the blockchain happy again, makes it more, makes the blockchain be happy to store this stuff again, then it can be replaced, like with exactly the same data as was there before. So a way that you could do this, and I think this is implemented actually in the Substrate smart contract palette, a way that you can do it is to remove this node, but introduce a new node that represents this node. It stores the hash of this node, but it's like a tombstone, right? It's like a sort of, this node used to be here, and it kind of still is here, but if you want to use it, you first have to sort of pay to put this data back. And the blockchain would not store this data, it would only store the hash of it. Yeah? So this would mean that you've now reduced your storage costs, as long as no one wants to use this bit of data, this bit of the trie. This doesn't work so well when you're hashing your keys, because of course this bit of the trie might refer to something for one user, something for a completely different user in a completely different application of the blockchain, and so on and so on. And it's therefore hard to throw away nodes that are sort of have all roughly the same reason to be there, and therefore reason to return if someone pays. But what you can use it for potentially is a system like a smart contract system, where it is all the same application. So it might be that this represents one smart contract, and then you can actually basically just remove all of this data, replace this with like a tombstone with the hash on it, and then if anyone ever wants to use this smart contract again, they just have to present these 4 leaves. And the blockchain can do the rest. The blockchain can hash them all and make sure the hash matches the tombstone, and if so, it can have all of the full nodes would now start replicating all this data, and it's all back to normal. And there are ways of doing it by through proofs of basically doing it in multiple stages in case this is a huge amount of data. You wouldn't have to do it all in one step. You could do it like 100 nodes at a time, 100 leaves at a time or whatever. This is all fine as well. You would just have to make a proof that you basically have to insert, you'd have to, in the operation, you might just replace these 2. You only have a tombstone for this one. Well, in the operation, the blockchain will be able to calculate this hash, great, just from the data that you're bringing in. It wouldn't be able to make sure that this hash is the first child of this node, right? For that, it would need this hash. So you'd have to present this hash as part of your proof that these 2 leaves are legit. But that's fine. I mean, you can do that. That's just a regular proof. So you give this data, and this hash. And the blockchain could partially restore this node. You'd also probably want to provide payment. Yeah, to make it in the blockchain's interest to bother storing this data again. There are most likely other ways of doing it where you're actually altering the Merkle tree format, its internal format. That would be a way of doing it like on top of so you wouldn't alter the internal format of the Merkle tree. You'd just alter the semantics for like what a tree, what this node meant. Like instead of, I suppose actually, no, ignore me. That probably would still alter the internal format. I guess you could do it by just sort of having a leaf, or having a node that ended here and represented a tombstone. There might be a way of like making a design so that you would not have to alter the Merkle format, the tree format per se, building it on top, but it would depend a lot on your original tree format in the first place. So I couldn't go into too much detail on that. But basically, tombstones, right? And a proof that the nodes that were thrown out actually are the real data for this tombstone.
Cool, thanks.
One more, you think?
Yeah.
If we have just a transaction of crypto from one wallet to another, what is the application of the Merkle tree in that case?
So if we are transferring from one wallet to another.
Yeah, just some crypto from one wallet to another.
Okay. Well, this depends a lot on the specific blockchain. In a blockchain like Polkadot. These nodes would represent balances of specific accounts. And in executing a transfer transaction, the logic would alter say these two nodes, person A and person B, and reduce the balance by person A and increase the balance of person B. But these two nodes change, which means their hashes change. So this one's hash, this hash changes, this hash changes, this hash changes, and this hash changes. All of the rest stays the same. And you'd end up with a new hash at the top, which is like the new database reference that refers to the change to the database after the transfer has happened. Yep. That's how Polkadot does it. So Polkadot is an account-based blockchain in that regard. There are other types of blockchains like Bitcoin that are not account-based. They're UTXO, so-called unspent transaction output. Basically, what they do is they store the public keys that represent funds that have not yet been spent. Hence, unspent transaction output. Funds that have not yet been spent are basically transaction outputs, right? So when there's a transaction, there's a bunch of inputs that must themselves be unspent transaction outputs, and outputs which become the new unspent transaction outputs. And generally, these are identified by the public keys. They're usually not, or reusage of the same public key is usually minimized. So usually we send them to different outputs than what their inputs are. Unlike in the account model, where accounts do tend to be reused over a long lifetime. Money goes in, funds go in, funds go out. They come in again, they go out again, they go out some more, they come in again. It's just a continuous reuse. Whereas with unspent transaction outputs, these public keys are basically all sort of anonymous pots, and funds go in, and then oftentimes all of the funds come out, get sort of combined with some other pots, and get combined with the output of some other pots and go into new pots. And it all forms a big sort of web, a big directed acyclic graph. In that case, your Merkle tree represents all of these unspent transaction outputs. And you prove that a particular input to a transaction is an unspent transaction output, basically just by showing that it exists in this tree. And it's the job of full nodes in systems that use UTXOs to basically store this tree so that they can very quickly verify a proof or verify an assertion that, A really is an unspent transaction output.
If a node is the hash of its two children in this case, then how would only a few nodes change in the case that you mentioned?
If A is, so going back to the account-based model that as used in Polkadot, if A is an account, B is an account, they're transferring, so A is transferring like 100 units to B, right? Then A, we can imagine under the node of A, it goes down from, 1,000 to 900, yeah? And we can imagine B goes up from 1,000 to 1,100, yep? So these two nodes have changed. A now has 900 in, B has 1,100 in. These nodes, the nodes are represented by the hashes of their data, right? So this node becomes, like the hash of 900, this is the hash of 1,100. Okay, so far. These guys, whatever they happen to be, other accounts, I guess, their data hasn't changed. Therefore, their hashes remain the same. This node is the hash of these two hashes concatenated. But these two haven't changed, so this, therefore, remains the same. These two haven't changed, so this remains the same, and so on across the rest of the tree. These two have changed, so this changes. Yeah, because the hash of these two hashes is which is, this one is the hash of 900, this is the hash of 1100. Well, the hash of 900 is different to the hash of 1000, so this has definitely changed since last time. Hash of 1100 is different to the hash of 1000, so this has definitely changed since last time. The hash of 900 with the hash of 1100 concatenated is different to the hash of 1000 concatenated to the hash of 1000. So this has changed. This is formed as the hash of the concatenation of this one and this one. Well, this one hasn't changed, but this one has. Yeah. Therefore, what it's hashing has changed, and therefore this node has changed. Same with this node, for which it's got one changed input and one unchanged input. Well, that's still going to mean that this one has changed. Same with this, because that's got one changed input and one unchanged input. That's still going to mean that this has changed. So the nodes that have changed are these two, this one, this one, this one, and this one. All of the rest, well, these two haven't changed. This one, therefore, hasn't changed. This one, therefore, well, these two haven't changed. This one hasn't changed, so this one hasn't changed, and so on. So we can ignore, I mean, not ignore, but we don't need to like have any special maintenance. We don't need to have any special maintenance going on for all of this part of the tree. The only thing we have to like maintain are, I mean, these two have changed, so we have to rehash them. We have to rehash this, rehash this, rehash this, and rehash this.